Hello everyone, and welcome to OneClass. My name is Fejiro, and I'm an Honors Bachelor of Science graduate, currently working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels, and I will be doing my best to answer them. If you need some extra homework help or just some tutoring, please check out the links in the description below. With that being said, let's kick it off for today with question number 1. Which is, what is the name of each compound? And let me just quickly switch my screen over. Alright, hopefully you can see me. And yes, we're starting with what is the name of each compound? So the first one we have Na2O. And then we have FeOH3. Okay? Both very interesting compounds, but let's see how we can get more information out of them. So the first thing I notice here is if we look at them, sodium and oxygen refer to our periodic table. Okay? And sodium is considered a metal, because on the metal side, if I hover over the metals, sodium should light up. Perfect. And oxygen is considered a non-metal. As I highlighted here, oxygen is considered a non-metal. And even look at the Fe. Actually, we're not going to look at that one because OH3 is considered hydroxide. Hydroxide, okay, because it's OH3, would also be, if you hover over the non-metals, we have oxygen, which is a non-metal. But we also have hydrogen here when it's highlighted, indicating that it's also a non-metal. Okay, the reason why I point this out is because we need to understand, in order to name it, that these are ionic compounds. Okay, and now because we know that, we can approach it with certain naming rules. All right, so Na, if we refer back to the table, is sodium. So we would have sodium. And then we'd follow that by, what would this be? Oxygen. Sodium, oxygen. Okay? And now, we're not done yet, but at least we have this. What we need to do now is abide by the rules when it comes to the, suffix of the oxygen. We need to change that. Drop the YGEN, and it'll be IDE. So for the first compound, we just have it named sodium oxide, okay? We'd actually have to do nothing more because it's actually been balanced out. Luckily, sodium is not a transition metal, which is what we're about to get into with iron. But because we know that sodium is just going to be Na plus and oxygen is just O2 minus, we need 2 sodiums to account and balance the 2 charge from the oxygen. Now for this, hydroxide actually is OH minus, only 1 minus. So for them to be 3 hydroxides here, for the iron, it needs to be Fe3 plus. Why is this relevant for iron? Because if you look here, iron is one of the transition metals. It has different states of oxidation, or at least it has different cations that it can have, so it's whether iron 2 or iron 3. So for now, what I'm going to put is iron 3. Okay? Whoops, sorry. I'm just going to put iron hydroxide. Okay? We're going to start here because okay, it is a transition metal. We need to now actually specify. Unlike the sodium hydroxide, we need to specify what type of cation we're dealing with iron. So as you can see, it has 3 electrons to give away. So we'd call this iron parentheses 3 hydroxide. That will be how you name this, because for the iron you have to account for the fact that is a transition metal. All of this though we solve based on the fact that ionic compounds need certain ways to address it. Just gonna make sure everything's plugged in, okay? And exactly, ionic compounds need certain ways to address it, which is why we did it as sodium hydroxide. Now, and sodium oxide and iron 3 hydroxide. So let's see how our colleague did it. Second, they have sodium oxide, perfect, and FeOH3, we have to specify iron 3 hydroxide. So that being said, this is correct. And we move on now to the next question here. Question number 2. For 2, we have how many atoms in the pictured molecule can form hydrogen bonds with water molecules? It's a picture with NCO2. So this is a very strangely worded one. Let's see here what our colleague said, because we're lacking the picture. So I want to be able to verify based on what they're saying. So a hydrogen bond, though, at least we can answer this. Okay, hydrogen bond. Okay, there's 3 types of hydrogen bonds that we typically deal with, all involving hydrogen. So I'll put that first. Okay, and these ones you do have to memorize so you can get as comfortable as possible. We have the one that we typically see, aka hydroxide, HO. Then we also have one where it's bonded with the strongest electronegative atom, which is fluorine, that's HF. And the last type of hydrogen bond would be HN. Okay? Now, with that being said, if we try to draw out NC2O, okay, so considering that nitrogen gives, that's 5 electrons, 5 valence electrons, 4 times 2, because carbon has 4 and there's 2 of them, has 8 valence electrons, and oxygen will be 6. So just to be able to visualize an idea of NC2O, maybe we can draw something to see what angles we can approach the hydrogen bond. Okay? So in total we have 5 plus 8 plus 6. So it's going to be a very weird looking molecule. Okay? Because NC2O, as far as I can tell, would be drawn extremely weirdly. My best guess would be NCCO, but it still would not be good enough because of the fact that it needs to be NC2O minus, because right now we have to share 19 electrons. Okay, if we had it like this, the issue we're facing is if we did a double bond with oxygen, okay, so nitrogen would be plus charge, but this wouldn't work here. We'd actually have to have one of the C's in the middle. The reason why I say that is because overall we want as much of it to have a, I guess, my concern is the C at the end, because this one is definitely not going to be properly, I guess, bonded. It never really was. Sorry, give me a second. Okay, and we're back. All right, so I do apologize for that. I'm sorry for the lagging. But like I was saying, this molecule overall would be very strange to draw. This is my best guess of what it would look like, something like that, and it'd have to be attached to more and more things. I don't think you can do more than that. I don't know how the star came on, but here we are. So, with that being said, though, what's going to happen here overall is that because hydrogen bonds are between the HO, HN, and HF, what this question is really asking, although it's kind of in a convoluted way, was which one of these things present in NC2O can actually form a hydrogen bond with the passing water molecule, which, by the way, is, give me a quick second here for the levels to adjust. I do apologize again. Hopefully it's a lot more clear. So, like I was saying, with the water molecule, which is like that, H2O, we have this. This is going to be flowing around and has the opportunity to either form a hydrogen bond with that or form a hydrogen bond over here. And that is really what we're aiming for here, is that this right here would be how many atoms in this pictured molecule that we don't have a picture of will be able to bond with the water molecule. It'd be the nitrogen here and the oxygen here, because according to hydrogen bonds, these are the three that participate in them. So hopefully that clears it up of what this question meant. And with that being said though, just like how my colleague said, nitrogen and oxygen atoms will be the ones to form the hydrogen bonds with water molecules, since it's very electronegative. Okay, so this is correct. Now with question number 3, okay, we have, what is the name of the compound with the formula? So name of compound with formula CH3 CH2 CH2 CH. I have too many, or nope, CH2OH. What is the name of this compound? Now, in order to get this name, though, we really have to focus on, I like to start with how many carbons there are, okay? So I like to start with how many carbons there are. So with that, sorry again, I don't know why it keeps cutting in and out. I like to focus on how many carbons there are. So with that, we have carbon, 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 carbon. We have 4 carbons according to this picture, okay? And what do 4 carbons mean? Well, let's just go through it. So we have meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. And each one is, so sorry, meth, to write that more clearly, is 1, eth is 2, prop is 3, bute is 4, which is what we need, pent is 5, hex is 6, hept is 7, oct is 8, 9 is non, dec is 10, okay? So we need bute, and when we have C4H2N plus 2, which translates to C4H10, we get butane, okay? Now, this OH, though, is what we call an alcohol group, all right? And when you have an alcohol group which replaces one of the hydrogens, as you see here, instead now we have 3 plus 2 plus 2 plus 2. That in total doesn't add up to 10. Instead it adds up to 9. Okay, we have 6 here and then a 3. We have 9 hydrogens now, and the last one's replaced by an OH, all right? In this case, it becomes an alcohol. Still keeps the same BUT in the front, but instead of the A and E, it gets replaced, and it's now BUT-ANOL, butanol. And with that being said, if you now look at what we're able to get and the answer choices we have, you will see the only choice we can really pick would be C. And that would actually be your answer here. This is an alcohol group, and we can say that it's butanol because there's 4 carbons in there, okay? And let's see how we did. The count of the chains, the functional group OH, which is alcohol, and therefore the answer is C, because there's 4 carbon. The longest carbon chain is 4, which is the only carbons present, and that has a prefix of bute. Give me a second. And like I was saying, that has a prefix of bute, so B-U-T. And with that being said, this is correct because we get the answer of butanol. Now for question number 4. For question 4, we have, what is the formula for aluminum nitrite? And then it asks, which of the following elements is noble gas? So first we have formula for aluminum nitrite. And then we have which is noble gas. So for this, actually, I would actually prefer if we started with the noble gas question, because this is a matter of going through the periodic table. We're given potassium, calcium, bromine, or krypton. All right? And with these choices, if we go to the periodic table, we can just quickly eye them out. Potassium is on the first column. That is known as an alkali metal. Calcium, second column, which is known as an alkaline earth metal. Then we have bromine, which is on column 17, which is also known as halogens, as you can see up there. And then as the last one, we have krypton, which is funny enough, as our periodic says, it's a noble gas. But the trick I really want you to learn here is that when you're dealing with elements that are on the last column, the 18th column, I guess except for argon neson down here, going all the way down to from helium to radon, those are your noble gases. So knowing that, actually, we can see that the choice krypton is the only choice we can make that would be the noble gas. So now going back to the question of the formula for aluminum nitrate. So for this, what I like to do is I like to write the pieces. So you have Al for aluminum. At least we know that much, okay? And aluminum, if we go to the periodic table, likes to get rid of 3 electrons to become a noble gas, or at least achieve the noble gas state. So we need an Al3+, okay? So at least we got that part done. Now nitrate. This is something that does have to be memorized, unfortunately. At least we know that it has a nitrogen, okay? And we deal with 8s. It means there's a certain amount of oxygens. I've memorized these, so I know nitrate is NO3, okay? That is what you need to know. Now, nitrate, you have to remember this is part tricky. It has just a charge of minus. NO3 minus, that would be nitrate. And because of that, give me a quick second. Okay, I think we're stabilized enough. Like I was saying, because nitrate is NO3 minus, and since aluminum is 3 plus, we would need 3 of these in order to balance out the aluminum. So we actually have Al NO3 3. Now that is what I believe nitrate is. I may be wrong, but let me just check my acids and bases sheet here in order to figure that out, because HNO3, perfect, NO3 would be the nitrate ion, which is what I was looking for to confirm. It is NO3 minus indeed. So with that being said, this will be our formula for aluminum nitrate because it has the aluminum and it has 3 nitrates, which is what's needed to balance out the 3 positive charges of aluminum. Let's see how our colleague did. Oh, I misread that. I'm just waiting for it to stabilize. There we go. And this is a perfect tangent because this shows the importance of rereading your question, because it did not ask for aluminum nitrate, it asked for aluminum nitrite. Subtle difference, but it's super crucial and it's important that you recognize that. And because we're dealing with aluminum nitrite, as I just saw from my colleague when he said it again, nitrite is different. Think of nitrates, but you get rid of 1 oxygen. So we have NO2 minus. So our answer simply just changes to NO2. Now, I would like to emphasize here, as I just did with the nitrate and nitrite, for one, it was an oversight on my part, but two, more importantly, nothing else changed. When you go from an 8 to an, I do apologize for this. Okay, when you go from an 8 to an 8, okay, you lose one oxygen, but the charge remains the same, the nitrogen remains the same, everything else remains the same, which is why we would actually just get this, AlNO2 3. So exactly, the nitrite ion, NO2 minus. That was my mistake there, and therefore the formula for aluminum nitrate, funny enough, they missed the actual aluminum part, but they do say the aluminum cation is +3. So it looks like we kind of just work together to formulate the answer, but this is what you should be getting here, okay? The AlNO2 3. Now with that being said, noble gases are on the 18th column, which is why krypton is the only noble gas there. Now with that being said, we got krypton, we have aluminum nitrite, and with that, this is correct. And now moving to the next question, question number 5. For 5, we have predict the molecular shape of IF4 using Vesper theory, and we want to answer all these questions here in order to, after we predict the molecular shape of IF4. So we're going to first, let me just do this actually, give me a second. Alright, we're back. I do apologize for that. Hopefully we'll be able to go on uninterrupted. But like I was saying, we want to predict the molecular shape of IF4 minus. Okay? So in order to do that, as I said, we need to start by drawing our best Lewis structure. So iodine, okay, would be on the 17th column. Same with the fluorine. So we're actually dealing with 7 times 5. So that's a total of 35 electrons plus 1 because of this negative. So we need 36 electrons to account for. So we're going to put the iodine in the center, okay? And then we're going to go ahead and draw the 4 fluorines attached to it, just like that. And now what we want to do is draw out the valence electrons on the fluorines at least, because we know that right now it's sharing 1 of its 7. So it'll be 2, 3, 4, 5, 6, 7, and the same thing, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, and 2, 3, 4, 5, 6, 7. So now we have this, okay? But iodine as well is sharing 4 of its 7. So it will be 5, 6, 7. Now iodine has an unpaired electron. We can actually fix that there we go. Okay, looks like it stabilized a lot better. So like I was saying, iodine has an unpaired electron, but we can actually fix that because, as it said earlier, we have a negative there, meaning we add 1 electron. And there you have it. This should be a Lewis structure, but let's go over a few checks to make sure this is possible. So yes, first of all, iodine definitely has an expanded octet, which is okay. It wants to do that. But let's see now with the rest of them. So fluorine, in order to have a formal charge of 0, likes to be just 3 lone pairs, 1 bond. Every fluorine is doing that. Iodine, funny enough, same thing. 3 lone pairs, 1 bond. But we can actually modify this picture by, in a sense, adding bonds to it to, I guess, get as close to the iodine as possible. So every lone pair can form 2 bonds. 1, 2. I'll be right here, just waiting for it to load up. Okay, there we go. So we have 1, 2 here and 1, 2 here. Okay, that would be what iodine could do as well to still keep the formal charge 0. But what's happening here is that instead of having 5 bonds in 1 lone pair, it has 4 bonds in 2 lone pairs. So it's actually replaced a bond with a lone pair. It's kind of like that, if that makes sense. And when you replace a bond with a lone pair, you take a step in the negative direction. That becomes your -1, which makes sense considering the fact that iodine, well, IF4 is it's an ion. It's an anion, which is 1 extra electron. That's where the extra electron is. As we just drew out, it's on the iodine, which makes the most sense in this case to actually balance out this molecule. So now that we've actually drawn the Lewis structure, what does the second step state? Count the number of electron groups, bond pairs and lone pairs, with multiple counting as 1 effective electron groups around the central atom. So the number of electron groups we have here are going to be 1, 2, 3, 4, but then it also says and lone pairs, 5, 6. We have 6 electron groups. Okay. And now, to establish electron group arrangements and then answer, from the electron group arrangement, you can determine the hybridization of the central atom to be, in this case, because we have 6 electron groups, it will be hybridization of sp3, that's 4, d2. The reason why, because think of the s as having it as like 1 coefficient, so it'll be like s1, but we don't really ever say that, it's just s. So that'd be 1, 2, 3. I do apologize for that because I do want to make sure we can follow along. Hopefully you can hear my voice. I'm just waiting for the stream to kick back up. Okay, there we go. We have S as 1, and then we have the P3, which is counts as 3 more, which is where we're kind of get to 6, and then D2, which is the last 2. And that would be 6 in total. So that's the hybridization. It will be sp3d2. And that means for this, the electron, I guess the electron hybridization, the shape would be known as, if I remember correctly, for this, it would be octahedral. Okay? That would be the name for it when it has 6 electron groups. Now, it says that the electron group arrangement is not necessarily the same as molecular shape. What is the name of the basis of this, okay? So with that being said, what we have to do here is we have to actually split the electron groups into whether they're lone pairs or actual bonds. In this case, we have 4 bonds, but 2 lone pairs. With this 4-2 split, the name actually is square planar. Let me just pause here, wait for everything to stabilize. There we go. So we have square planar. What does the shape look like? Well, it kind of looks like this. We have the iodine, the lone pairs, and it kind of looks like that, where the fluorines are all kind of circling like that. I want the best 3D structure to think of is kind of like that, with an electron on top and the bottom, kind of like a line going through it. And if we were to look at it as a plane, it would be like that for the fluorines and this for the electrons. So there'll be electron up top here and down there. This is kind of what it would look like. We can actually refer to our VSEPR sheet here. As you can see, we have for 6, it's known as octahedral, sp3d2, perfect. And we have 4 and 2, square planar, and that's what we're dealing with here. Now they also ask for the ideal bond angles around the central atom, and that would actually be, at least specifically for the other atoms, a 90-degree angle. The electrons are doing such a good job of distributing it is that it's literally flat. So the fluorines now have the space to be evenly spread out from each other, which would be a perfect 90-degree angle. So they're all 90 degrees apart. That would be the best arrangement, okay? And now I'm just reading through. By analyzing repulsive forces, the only bond angles can actually be observed, and to predict if any deviations will occur. There's going to be differences, I guess, where they're saying that the experimental bond angles might be slightly different than what we predict, but in this case, I do anticipate that it's going to be most likely the ideal bond angle of 90 degrees. And then it says, taking the vector sum of the dipoles, we can evaluate the net dipole movement. And for this, as you can see, based on how we've drawn it in several ways, if we have a dipole movement going in every direction, overall, we're just going to end up with they all cancel each other out, especially because they're all fluorines, so they're all pulling each other equally. So in this case, funny enough, this would actually be a non-polar molecule. So for this is more of a discussion than an actual question, but with that, I hope you can see how we first went with Lewis structure, and then we broke it down piece by piece so to get the shape, the molecular geometry, the angle differences, and whether it will be polar or non-polar. Let's see what my colleague has to say. Exactly just the shape that we got. Perfect. 36 valence electrons. We do have sp3d2. Awesome. Molecular geometry is square planar, and the bond angles between the axial and equal is 9 degrees, like that. For equatorial atoms, the bond angle is 120 degrees. For that one, doesn't really make much sense. I don't know where they got in their other 120 degrees from, because it should be all 90. Even technically from the lone pairs to the fluorine, it kind of be a 90-degree angle like that. So I'm not sure where the 120 fits in. But is that the VSEPR theory? Let me just read over these. Exactly, they repel each other, and it's like we do want the 90-degree angle. Not sure what they mean by equatorial, because it can't be 120, because then you'd be picking something like this, and that's not what we have at all. We have 4 of them, so it's definitely all 90s. I'll give them the benefit of the doubt. I think they definitely have a different shape in mind. I can't think of a VSEPR theory that really abides by that, considering that we have all these different shapes and none of them really have a, maybe like the seesaw, but that's not what we're dealing with at all, or even the trigonal bipyramidal. That may be what they're thinking of, which is not the case here. It would actually be, give me a quick second. Alright, I do apologize for that. Hopefully it's stabilized more by now for the stream. With that being said though, like I was saying, unless you're thinking about like maybe trigonal bipyramidal, which is not the case at all. That's where I can think of where we have 120 in plane and then 90 above and below, which is also not the case here. So I will still give them the benefit of the doubt here. But I do want to stress that everything should be 90 degrees. I wish I had a picture of the actual molecule rather than just a Lewis structure. But at least let's see what it says about the dipole movement. With this being said, it does say that IF4 is indeed nonpolar, which is exactly what I was looking for. So although the bonds may be polar in itself, because fluorine is quite an electronegative atom and iodine is not that electronegative, so by comparison fluorine would create a polar bond between it. Because they're all polar bonds pulling equally apart as I drew, it would end up being a non-polar molecule. Okay, so that being said, I'm just going to say this is correct, although all angles are 90 degrees, at least from what I can see. Based on every picture I draw, I cannot understand where 120 degrees would fit. Maybe I may be wrong in this case, but at least from my opinion, all we have here, as the name implies, square planar, only 90-degree angles. So now for question number 6. So for question 6, we have, what is the Lewis structure for CF4? So I'm just gonna, as you can probably see the drawing made by my colleague, it paints a pretty straightforward picture of what the Lewis structure of CF4 is. Nonetheless, we're going to try to solve it as if we did not see that. So with that being said, carbon, okay, is on the 14th column, so it usually has 4 valence electrons. Fluorine, on the other hand, being on the 17th column, we're working with oh, I think I might see the issue now. Okay, well, that's just a side note. But fluorine, yes, working on the 17th column, has 7 valence electrons. Multiply that by 4, and we get a total of 28. I believe 7 times 4. Add together, we're dealing with 32 electrons. So if I did this, C, F, 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 we have, sorry, I just started filling in right away because I was going to take the picture, but let me explain what happens here. I drew one bond between them, but what now I want to do is account for the valence electrons of fluorine. Fluorine is right now sharing 1 of its 7, so it'll be 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, and 2, 3, 4, 5, 6, 7. And carbon is already sharing 4 of its 4, so carbon is done. It can no longer do more than that. So in order to get the Lewis structure, I mean, we've pretty much done that, but to verify if it's correct, what we can do is see if actually they're all at their formal charge of 0. So carbon's formal charge of 0 is represented usually by a carbon with just 4 bonds. Fluorine, on the other hand, needs to have 3 lone pairs of 1 bond for it to have a formal charge of 0. Thankfully for us, that's what both the carbon and the fluorine are doing. So in this case, this indeed, just like our colleague drew, will be the Lewis structure for CF4. So with that, this is correct indeed. And we can now safely move on to the next question. So question number 7, we have, what is the molecular formula of butane? So I do wish you could not see what our colleague said, but we want butane molecular formula. So with this, actually, the way we would approach this I see. Okay, give me a quick second as the stream stabilizes. Alright, so with butane, as you recall, we want to know what each of the prefixes, so the BUT stands for, and also the suffix as well, but we'll start with the prefix. So we have meth, eth, prop, but, so that's a big hint right there, pent, hex, hept, oct, non, and dec. And each counts for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and that is actually for the amount of carbons we have. Okay, so based on that, if we have butane, well, but is 4, we know we have C4. Now, for the A and E part, that means that our chain is saturated. What does saturation means? It means that our form can actually fall here, where it will be H2N plus 2. What is N, you ask? If we replace a C4 with Cn, that will clear up what that is. So considering that N in this case is 4, H would be 2N, which is 8, plus 2, 10. So that would be C4H10. Because of the specific fact that when it's butane, A means that it's saturated, all the bonds are filled. Give me a brief second. Exactly. So A means it's saturated, all the bonds are filled. So we have this 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Think of those little spikes as where the hydrogens are. And these parts here are where the carbons are located. Hence how we get butane as C4H10. And this is correct. And now for the next question, number 8, we have draw the Lewis structure for sulfur hexafluoride. Okay, so Lewis for sulfur hexafluoride, and they generally give us as SF6. So before I continue, just with the name SF6, you should be able to identify what type of molecule we get. We have sulfur hexafluoride, and hexa in this case would mean 6 of them. And based on the naming rules, give me a brief second. Alright, waiting for it to stabilize here. And we're back. Okay. Alright, so like I was saying, the Lewis structure for sulfur hexafluoride, for the sulfur hexafluoride part, based on the naming rules for, I would say, nonpolar molecules, this actually follows it. Because we have a sulfur, and we have a hexa, meaning 6, and then fluoride follows after, meaning that we need 6 fluoride. Hence how we get SF6. So with this though, sulfur is actually on the 16th column, so that means it would have 6 valence electrons, and fluorine would be on the 17th, meaning it had 7 valence electrons, but there's 6 of them, so we need to do 7 times 6, which is 42, plus the 6 offered by sulfur, so we need to account for 48 whole electrons. Now, that's what we did for step 1. For 2, we need to find a total number of electrons to make the atoms stable. So what I like to just start with the middle, sulfur, and we can do 1, 2, 3, 4, 5, 6. I'm just going to put the fluorides on each one. And now what I'm going to do here is I'm actually going to fill out the valence electrons. Fluorides are sharing 1 of its 7, so it'll be 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2. Just pause here so you can follow along. But I'm just going to be reading to make sure I'm not missing anything. Okay. Waiting for it to stabilize here. I do apologize for the fluctuations. Hopefully this will not happen again. Alright. Okay. Now we're stabilizing. So now we have 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7. So that would be all of our fluorines there, which is their electrons. And for sulfur, it's funny enough, it's already sharing 6 of the 6 electrons that it could carry. So we don't do anything for sulfur. Now let's just quickly check if their formal charges are good. So for fluorine, it likes to have 3 lone pairs and 1 bond, which is every fluorine is doing here. But sulfur, on the other hand, likes to have 2 lone pairs and 2 bonds. Okay. Alright, so like I was saying, sulfur likes to have 2 lone pairs and 2 bonds. But what we could actually do is convert each lone pair to 2 other bonds. Like that. And I like to do this trick because this actually tells me that even in this form, it has a formal charge of 0. So both the fluorine and the sulfur in this case have a formal charge of 0, which is what we'd expect because there is no net charge involved, which is great. Now let's just confirm if we actually have the right amount of electrons. So for every fluorine, there's 3 lone pairs, and because there's 6 fluorines, we have 18 lone pairs, and we have 6 bonds. So in total, we have 24, I guess, electron groups, which is electron pairs. So 24 times 2, we do indeed account for 40 electrons. So this would actually be the Lewis structure for sulfur hexafluoride. And there you have it. Voila. This is correct. And now let's move on to question number 9. For question 9, we have the Ka for formic acid is 1.8 times 10 to the negative 4. What is a pH for 0.35 moles of an aqueous solution of sodium formate? So for this is going to involve quite a bit of steps. The first thing we want to do actually is write out, this is actually going to be very tricky because we want to actually get all the information without messing up here. We first need to, I guess, write a shorthand of what the question is asking. So we have HCHO2, Ka is 1.8, so I'm going to let this load, but I'm going to be writing it down as it loads. Okay, so I do apologize for the abruptness. We have 1.8 times 10 to a negative 4. It's going to load on your screen soon. And then we want to know the pH for actually its conjugate base, which is NaCHO2. So we can actually just write it as CHO2 minus. This is what's going to happen when it dissociates in water. It's going to separate between sodium and that CHO2. And we want to know of 0.35 moles of this. So the actual formula we're working with here is going to be CHO2. Let me switch colors for this part. CHO2 minus plus H2O, so that's aqueous liquid, turns into HCO2 minus, sorry, bad habit, HCHO2 aqueous plus OH minus. Now here's the tricky part though. We're given the Ka, but this OH would actually be using the Kb. You're probably wondering, how do we get from Ka to Kb? The same way actually how we get from from pH to POH. Because the acid and the conjugate base are like related like that, whatever Ka value is going to be, that multiplied by the Kb will give you 1 times 10 to the negative 14. Or in more simple terms, if you turn the pH to pKa, the formula you get is that if you turn the Ka to pKa, the formula you get is pKa plus pKb has to equal 14. How do you get this to now pKa? We would actually do, same way we get the pH, it would be negative log of Ka. Let's put that in the calculator. Negative log of Ka, which is 1.8, negative 4. The pKa for this is around 3.74 pKa. So if pKa plus pKb is 14, then 14 minus the pKa is pKb. So 14 minus that answer we just got. Let me just quick clear. 14 minus that answer, we get 10.25. So pKb is equal to 10.25. But we don't want to work with pKb. Well, 10.26 technically if you round it. We want to work with the Kb. So then here we'd actually use a formula of, as it loads, I'm just going to be writing down these equations. I'm going to pause so that we can actually get the equation. In this case, we're going to have, let me just check over this, pKb to get to pKb back to Kb, it would be 10 to a negative pKb. Hope you can see it pop up to my screen. Okay, perfect. So that is 10 to the power of negative pKb, so negative that answer, and we get the Kb, okay, which is what we want to work with officially, because that tells us the I guess the, not the rate of the reaction, but more so the amount it would be ionized. That's what we're looking for, the amount of ionization. Kb, it's 5.55, well 5.56 times 10 to a negative 11. So now we have our Kb we can actually use with the formula above. Now we've done that, we need to set up an ice table. Okay, initial, change, equilibrium. So with that being said, we started with 0.35 moles. That's quite a big amount compared to the Kb, which will play into effect later on, as you'll see. Initial is 0.35, and we're assuming we're starting with 0 for the other parts. We don't include water because water is part of the solution. It's not the solute, it's a solvent. We don't include water in there. But we do have one for the HCHO2 and the OH minus, okay? So with that being said, now we have 0.35 minus X as a change, because in this case, for every piece it loses, as you can see based on this formula, it's a 1 to 1 to 1 ratio. For every one lost here, one of each is gained. So that'll be X and X here, well, plus X. And then in the total equilibrium is going to have X's, and here this is where it now plays into effect. Because the 0.35 was such a big number compared to the Kb value, we have a rule. If it's more than 1,000 times greater, the concentration, if the concentration is more than 1,000 times greater than the Ka or Kb, we don't factor that in. It's negligible. So we really just have almost 0.35 again as the equilibrium. The reason that plays into effect because the Kb formula is similar to Ka is going to be OH times the conjugate acid divided by the conjugate base. Okay? So now with that being said, we fill in, it's just going to be x squared because the OH and the conjugate acid, which is 2 x's. And then the, give me a quick second. In this case, I'm going to fill it out as we go, although it's going to be a little bit more choppy. The KB in this, the denominator in this case, is just going to be our conjugate base, which we have, which is a 0.35. So we have 0.35. Hopefully it'll be stabilizing. So that means KB is equal to that. So KB multiplied by 0.35 will be x squared. The square root of that would actually give us x, which is what we're looking for. So we have now times 0.35 for that KB, square root of that, and then we get this really small number, which makes sense. Okay, x is equal to 0.00. Well, actually, let me just do this as easier. 1, 2, 3, 4, 5, 6. We get 4.41 times 10 to the negative 6. That is how much OH is produced. Okay, that is a theoretical P. Well, not POH just yet, but that's how much hydroxide is produced. And that would actually give us our POH. Once we do the negative log of that, we would get the POH. So in this case, the POH would equal negative log of the answer. We get 5.36 around there. Okay? But we're not asking for the POH. We want the pH. So with this, we still apply our same rule again. 14 minus the POH would equal the pH. So in this case, 14 minus that answer, we finally get a pH as our final answer of 8.64. Now, as you can see with this question, a lot of steps were involved. The reason why I'm going over it is because it's important that we need to work with the material given. We were given the Ka for the formic acid, but we're given the molarity of its conjugate base. So we need to work with the Kb. We don't know how much conjugate acid we have without using the Kb value to actually see how much it dissociates. So with that being said, that's how we did that. And then once we were able to now find our ice table, we were then able to now more properly, sorry, give me a second. Don't know why this one disappeared. There we go. We were then able to now properly get the concentration of the OH minus, find the POH, but then remember the question was asked for the pH, which is why we then converted back. Okay, so as we can see here, they got the same KB as us. I'm going to scroll a little bit slower as it stabilizes. We have KB of 5.56 times 10 to the negative 11. And then it went on to solve it, which is perfect. That's exactly what we did. And overall, they make sure that it says KB, not KA. So that's just make sure you check over your work. But overall, their concentration of OH minus should be 4.4 times 10 to the negative 6. And then they calculate the POH, which is 5.36. So then the pH would be 8.64. So with that being said, this is correct. And you can see here how they also broke it down step by step as I did to get that answer. So now as the last part, we want to do question number 10. For questions 10, we have what is the ground state electron configuration for nitrogen? Ground state E-config. And unfortunately, you can see the answer right there. But nonetheless, we're still going to pretend like we didn't see that. With that being said, we want to apply the off-ball principle. Luckily, I can actually walk you through each of the, I guess, quote-unquote, orbitals to make sure we get the nitrogen. So nitrogen is the seventh element, okay? That's what we want to account for. So we have 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then we have 2p, 3p, 4p, 5p, 6p, 7p. Then we have 3d, 4D, 5D, 6D. Then we have 4F and 5F. We're not going to get that far, but I wanted to lay out everything as much as possible. So now when it comes to counting these orbitals, remember we want to get to the 7th element. The first element, hydrogen, that would be 1s1, okay? Because that's the first one, that's the s orbital. And helium, this is where the only exception is because it's actually on the right side. Helium, although being a noble gas, that would be counting as your 1s2. So now we've actually cleared the obstacle of the 1s's, okay? Now to get to the 2s2, we have lithium will be 2s1, beryllium will be 2s2. So we're done with now that orbital because of the fact that s orbitals only take 2 electrons because only one orbital. And we're done there. So that would mean done. And now we get to the p part, where it's boron, carbon, and nitrogen. So we're actually quite close. Boron will be 2p1, carbon 2p2, and nitrogen 2p3. And the reason why I mentioned the 7th electron, because as you can see here, these coefficients, not coefficients, these superscripts, they should add up to 7. 2 plus 2 plus 3, it does indeed add up to 7. And to clarify what they mean by ground state is they want a nitrogen element. They do not want a cation or an anion, they just want the nitrogen elements. So with that, let me just slowly go over to what my colleague said. As I said, we have 1s2, 2s2, 2p3, just like how I've written there. But if we go back to here, as it should now have loaded for you, just as how my colleague got, it's 1s2, 2s2, 2p3. So with that being said, they just explain how they got it, and exactly because the ground state nitrogen has 7 electrons, it needs to fill in the orbitals accordingly. Hence how we got 1s2, 2s2, 2p3. With that though, this is correct. And that should be our last question. Okay, so once again, I just want to thank you for joining me tonight. I do apologize for the streaming errors and issues that we faced. Definitely going to get that looked and fixed. But with that being said though, you have a lovely rest of your night. And see you next time. But I do want to emphasize again, any of the topics I covered, if you just wanted some further clarification or some extra help, please do check out the links in the description below. With that being said, thanks again and see you next time.